Piyush was saying, I have done past work on probabilistic programming. And in fact, actually, when they invited me, they asked me to talk about actually my work on probabilistic programming. But actually, this is a more recent thing that I'm doing, and my mind is much more in this right now. So I thought I'll talk about this. And I think it's quite interesting, and I hope to convey why. I can get going? Okay, sounds good. So how many of you have heard the term program synthesis before? Just get a show of hands. Okay, only like one. So I think one thing I will do is actually I will assume no background in program synthesis, and I'll actually introduce it, right? But this talk is actually about the intersection between program synthesis and machine learning. I will give a gentle introduction to program synthesis and particularly supervised machine learning from a PL person's viewpoint. And then I'll talk about our work called HDEF. And then finally, I'll talk about other people who work in the same space, not just me, at the intersection of program synthesis and machine learning. Okay? So program synthesis is a quite old area. One of the earliest papers I know of is this paper in 1957 by the same church who came up with lambda calculus, recursive functions, and so on. It's the same church. And it's a very interesting paper. It's available on the web. You can download it today and read it also. And what the paper says is, it actually was one of the first references to program synthesis. And Church defines the problem as you are given a logical relation, phi xy, a formula, where x is an input and y is an output. And given such a relation, he asks the question, can I automatically synthesize a function that given x will produce the output y? That's the question he asks. And he conjectures, so the goal is to construct an f, construct a constructive proof of that logical statement. There exists x such that for all, exists f such that for all x, phi x fx, where phi is the same logical relation. And then he says, then the process of synthesis is to actually discover or construct such a function f. And he conjectures that for formulas written in certain logics, and he in the paper talks about these things called monadic second order logics, he conjectures that the synthesis problem should be decidable. I guess that was a good time to write such a paper, and that's the entire paper. He says, I have an intuition that for phi, just in these logics, it should be decidable. And the paper just ends there. And this was worked upon for many years after that. And I think the first proof of that conjecture was done by Bucke and Landweber in '69, and then by Michael Rabin in 1972. And this actually is a very interesting paper. I have read this in grad school. This is one of the earlier papers on these things called tree automata. And that has to do with strategies and so on. It's a very fascinating paper. But the interesting thing about all of these procedures is that they, at best, are p-space or exp time. At worst, they can be not, some of these algorithms are non-elementary. And I was actually at coffee break describing what a non-elementary algorithm is. A non-elementary algorithm is one in which if the input is n, of size n, the time complexity of the algorithm is like this, where you cannot even bound the number of exponentials by a polynomial function of n. So this was actually far from practical. But I think the story that I'm going to tell you is that this area has become intensely practical in the recent years. And the reason why that has happened is by a reframing of this problem so that you look for you constrain the space of functions that you search for. Right? So instead of these functions being from a very unbounded space, there are things you can do to make the space of functions to be finite. And once you make this to be finite, I mean, the problem just becomes a decidable problem, and it becomes a search problem, and it becomes intensely practical. Right? So, and this was actually first done by Bodic and Lasama. Lasama was doing his PhD thesis at Berkeley, and he came up with the notion of a template or a sketch, which is sort of a framework that is given by the user, by the programmer, to constrain the space of functions, and then you search for functions within that space. And a colleague of mine, Sumit Gulwani in Microsoft Research in Redmond, came up with a system called FlashFill, also by constraining the space of functions using what is called a domain-specific language, which is a grammar that you can give, and you just search for programs that are bounded trees within that grammar. So by doing these kinds of restrictions, synthesis now becomes a search problem. Desirability is no longer an issue. Efficiency is the main issue. And whether you can actually generate useful programs that are useful for various purposes becomes the issue. The community has now, this has caught on like wildfire. This is SIGA stands for Syntax Guided Synthesis. This is a competition that actually happens every year. Benchmarks are given, and many people compete. And this is very vibrant, practical area. I want to give a sense for how this looks like. To give you an example, I wanted to give you this motivating example. This is a program that transforms bit strings to bit strings. Think about 16 or 32-bit words. I want to transform them. And the job is to take the bit string, take the rightmost sequence of contiguous ones and reset them to zeros. So this one is reset to 0. This one is reset to 0. Here, the rightmost contiguous have 2 ones, and I have to reset them both to 0. It's clear, right? What I want to do. Now, I want you to write a program which does this, but I won't allow you to use a for loop. If I let you use a for loop, there's no fun in this program. I will allow you to use only word-level arithmetic and logical operations. You can do bitwise OR, bitwise AND, negation, plus and minus, which I guess overflows or underflows, left shift, right shift, constants. This is all that I'll allow you to use, and I'll ask you for a program of a tree that is bounded by, say, 5. Right? That's a finite space of programs, and I will ask you to find a program which does this. Right? It turns out that if I don't say contiguous ones, that is actually a very easy program. If it's the rightmost one that I want to reset, what would be a program? Can anyone guess? I think this program would work. I think something like this. I don't remember minus or plus. One of those I think should work. So if I actually add 1 or subtract 1 and then AND it, it turns out that the rightmost one gets reset. And this one is a little bit more tricky and impressive, and actually that's the program that resets the rightmost contiguous sequence of ones. And you could actually check it. In fact, actually, you could even prove that this program does that using theorem proving and so on. You could actually do that. Here's a different one. Here you have a spreadsheet, and in the spreadsheet, how many of you use Excel? I guess no mathematicians use Excel. Maybe I think you must be administrators, managing budgets or something like that, right? And in Excel, there are these things called macros that you can actually use, and those are just small programs where suppose this is one, and then here you somehow have to combine these columns, maybe like a last name, something, and the intention is that you want to do this for all the rows, right? And Sumit Gulwani built a tool which, given just this one example, will synthesize a macro which does this. And actually, I wanted to show you something which I find incredibly impressive to sort of get a sense for actually how well this works. Can you see this? Is it big enough for you to see? So this is an Excel spreadsheet of the US presidents. And let me show you what I'm doing here. So I'm doing something like this, and here's what I'm doing. So I'm actually just going to, so this is actually how you copy a row. So it copies Washington, Georgia, and then if I just click here, there's actually something called flash fill. And you can just see something amazing that it has done. So what it has done, do you see what it has done? It has actually now, instead of copying, it has actually synthesized a program. It has actually understood what the transformation is and synthesized a program. Let me play with it a little bit more. Now there's this guy, William Henry Harrison. He has 3 names. All the other guys, maybe, many of them have only 2 names. Maybe I'll just say William. And you can sort of see, you can see the other ones with 3 names are actually now getting updated. And this maybe has some issues, I don't quite know. So, but you can sort of see how this kind of works, right? So this is program synthesis in action, where you give a grammar, and the job is to, and you give some specifications, which could be the formulas are examples, right? And examples actually are like formulas. I mean, they're not very different from formulas, because if I give you an example, like, if input I1, I have to produce O1, and I2, you produce O2, the way you write Phi xy as a relation is that if x equals I1, then y equals O1. And if x equals I2, y equals O2, and this is the formula. And if x is something else, you're not saying anything. So examples can be thought of as formulas. It's not a big deal. But here is, I now ask for forgiveness because I'm going to describe machine learning from the perspective of a programming languages person, right? So if I want to compare this to how supervised learning works. In supervised learning, you are also given input-output examples, much like program synthesis. And you are trying to learn a program of the form AX plus B. So this is the domain-specific language. And you are learning two parameters, A and B, that most fits the data. And these things are quite popular these days. And here the only difference between this and this is that instead of learning 2 parameters, you're learning many, many more parameters. There's non-linearities in here, but you're given training sets, and you're trying to learn parameters that minimize a specification, a loss. And the specifications here are actually just loss functions. And in some sense, the domain-specific language is just the schema of the model. But the interesting thing is the search techniques that you typically use are continuous optimization methods like gradient descent. So I now have this sort of view of how, as a PL person, I think about these 2 things. In the program synthesis, I sort of think about specifications as logical formulas or a small number of examples. And the domain-specific language is also an input into the problem, which is the way in which you constrain the space of programs. And in the machine learning space, you typically have a much larger amount of training data. I mean, here you typically have only a small number of training examples, sometimes 1 or 2. And you're also given a loss function, some schema. And then here, the search function is a combinatorial search function, and here it's a continuous optimization. The output here is a program which satisfies the specification, and here it's something that minimizes the loss. And that's quite important to understand. And because it minimizes the loss, these kinds of techniques are much more robust to noise, in the sense that even if your examples are not exactly right, it's, everything just goes into a function that you minimize. And here, these kinds of techniques have a lot of difficulty handling noisy data. And the other characteristic that's very interesting is that in synthesis, what you produce is interpretable. You can even control the expressiveness by the kind of operators you want to put in, and you can get the kind of programs you want. Whereas these, particularly the deep networks, tend to be very non-interpretable. By that, what I mean is that you just learn a bunch of parameter values for all these kinds of things, and these will all be real numbers, and what this function exactly does is kind of unscrutable. What it will produce when you produce a new input is actually also unclear, right? So the interplay between program synthesis and machine learning comes from the following question, which is, these 2 definitely seem complementary, noise and then expressiveness. And can we combine the strengths of these 2 approaches, and what problems can you solve by this combination? So that's the question I'll start with. And I'll first show some work that actually I've been doing with some colleagues, and I forgot to call out their names. They're all, my collaborators at Microsoft. We've been working together for some year and a half, 2 now, working on this problem called heterogeneous extraction. I'll explain what heterogeneous extraction is. So here is heterogeneous extraction. You are given a sequence of records, a list of records, and the records are very unstructured. So this data set is a data set of politicians who stood in elections, Indian parliamentary elections. And I got this from a professor at Ashoka University. They have a center for political data, and they shared this data set with us. But each of these are in different formats. Like, for example, this person's father's name is something, their date of birth is something, and so on. And here, there's no father's name, there's a son of, and then there's something else, and there's no date of birth, it says born at something else. So you can sort of see the same information is there, but in various formats. And the idea is that you want to extract all these fields, father's name, date of birth, and then put them in a spreadsheet. That's the goal. Let me tell you a different problem. It's the same kind of problem, which is that these days you might all get emails about your flights. That when you book a flight, either from an airline or from an aggregator like a Clear Trip or an Expedia, you will get an email like this. And it's interesting to extract from this email who the traveler is, what the flight number is, what the arrival time is, what the departure time is. And if you can extract that, you can do very many interesting things with it. For example, my email program in my phone automatically pops up a widget every time there's a flight that I'm traveling. Many of you, might, and then I can click on it and directly check in. How many of you used such an experience? Some of you. I think most popular email programs provide this, right? And if you might actually think about how one might implement such a program, and the reason why it's difficult to implement such a program is that the number of airlines is large, and we don't control how they send the email. They can change the format of the email without telling us. And we need a system that keeps working even though the formats of those emails keeps changing. In fact, actually, this area is a very interesting area. It's actually called machine-to-human email, which is sent by a machine to be consumed by a human. And machine-to-human emails and how to extract interesting entities from them is a very interesting problem. It has many, many applications as well. So coming back to this problem, one of the interesting things about this problem is that this is the kind of problem where it's okay to not extract the information, but it's really bad if you extract the wrong information and then show that your flight actually leaves 2 hours later than what it actually leaves. That would be a really bad thing if that would happen, right? So that's a very interesting kind of requirement for these kinds of problems. And because of that, I can sort of tell you that I know people who implement this inside our company. They don't use machine learning precisely for that purpose, because actually if you use machine learning, it's unclear what output will produce, particularly the input changes. And that would be a bad thing. So the way people use this machine learning is that they use machine learning only to do clustering. You get millions and millions of emails, you cluster them into clusters, and for each cluster, you manually annotate what the expected output is, and then, because these are HTML, you use actually, there's a tool called WrapStar that people use to synthesize these kind of wrappers, where, again, actually, if you have ever seen how an HTML looks like a tree, and the kind of script that you extract is actually you walk down some path, and then you say, okay, so the flight number is in this particular path in the DOM, where the color is red, and inside that is the flight number. And of course, this is bad because if the person changes his name, the color from red to blue, then the script doesn't work anymore, right? And that's kind of unstable. And some colleagues of mine have been working with this team to mainly help them with clusterings, and then we thought actually maybe we can help them with program synthesis as well. And the high-level idea is that you could solve this problem using 2 means. One is actually you could come up with a machine learning model to train a machine learning model and produce an output. And the difficulty with this one is that it's uninterpretable. Because it's uninterpretable, that's a huge risk in actually building such a solution. The other approach is actually, WrapStar is an example of a synthesis system, right? Because it is producing a program. But the difficulty with this one is that it is non-robust, in the sense that if the inputs change, then I have to regenerate the program in order for this to work. So the idea is that, so the aspiration is that, can I produce a system that is both flexible and interpretable? In the sense that if the inputs format change, new airlines come, I shouldn't have to do manual work, but at the same time, I need to be able to inspect the program and understand what it is doing, and so on. Does it make sense, what I'm saying? So far, so good? Okay. So this is basically what we want to do. And the first idea to do this would be to see whether I can actually just daisy chain them, in the sense that you take an ML model and sort of feed this into a synthesis system, and then can you produce programs? That is the first thing that one might want to try. That's a reasonable thing to try, but there are some problems with it. So that's what we'll do. So we will take these labeled inputs, training set, and generate an ML model. And then the interesting thing, actually one other interesting thing about systems like this is that you often don't have much labeled data, right? So you might have like 1 million emails, and it's impractical to annotate a large fraction of them. So you end up annotating only a small number of them. But even though you annotate a small number of them, with the machine learning model, you can actually take the unlabeled inputs and then produce tentative labels from the machine learning model. But these tend to be noisy because we don't know, how much the machine learning model has actually even captured the true nature of this data. So, and we take the noisy labels and feed it to a program synthesizer. And the other thing that's interesting about the system is that, unlike the president's example I showed you, this has a combination of a clustering problem and an extraction problem. In the sense that this input has many, many clusters, and I don't even a priori know how many clusters are there, right? And we sort of need to generate different programs for each cluster. Because different airline formats look different. Maybe in every different state, the politicians are actually written out differently, and we don't a priori know what those are, right? So this is a clustering problem followed by a synthesis problem, right? So as a result, you cannot generate one program, you have to generate many programs, one for each cluster. And then you have to somehow handle noise, which synthesis methods have never really handled noise before, right? So in order to daisy chain them, right, I need a new program synthesis system that can handle clustering, and it should also be able to handle noise. And it turns out actually with basic techniques in probability, things like sampling and so on, you can actually build such a program synthesis system, and that's what I'll describe next, right? So how do you do this? So you take, now I'm going to show you this box where you take noisy labels and build a program synthesizer that synthesizes a set of programs, one per cluster. So how do you do that? So here's actually a diagrammatic way of understanding this algorithm, which for whatever reason is called NDSyn. It stands for noisy disjunctive synthesis algorithm. The input is noisy, and it's disjunctive synthesis because the output, is a set of programs. And people in formal methods call sets as disjunctions because it's A or B or C. A is a program, B is a program, and so on. So that's why it's called NDSyn. And here's actually sort of a cartoon to describe how this algorithm works. Think about this as many, many inputs. And the algorithm doesn't know what these inputs are, but since I'm sort of I'm doing a commentary about the algorithm, I know. So what I've done is that I've colored the inputs based on their cluster. So there's two clusters here. There's a blue cluster and a brown cluster. And since the outputs are produced by a machine learning model and it's noisy, some of these labels are even incorrect. And that I'm denoting by this dashed line, means that the input could be incorrect, right? So how does this algorithm work? We're going to repeatedly do sampling, and we're going to have a small number of samples from these millions of labels. And suppose that the two samples are from the same cluster. So when I generate two samples, I might get them from the same cluster, I might get them from different clusters, I might get two noisy samples, I might get one correct sample, one noisy sample, all of those things are possible, right? So what I'm going to do is that I'm going to take the small sampled inputs and I'm going to give them to a program synthesis system. The system that Gulwani has built is called PROS, that's what we use. And typically when you give a small number of inputs, it's very underspecified. There are many programs that can satisfy the specification, so the program synthesis system produces many, many candidate programs. So in this case, maybe it produces 3. And then we sample again, and here it turns out that we have selected one input from a blue cluster and one from a brown cluster. And here, what we are going to do is that by arranging, because we can constrain the domain-specific language, the language from which the programs were chosen, we can arrange it so that there is no feasible solution for this problem. Right? We can arrange the programming language in such a way that there is no program that can handle both these inputs. It is possible, and I'll show you how to do that. So as a result, I can actually arrange it so that no program can be generated. And now I'm going to do another sampling, and here I have one correct input and one incorrect one because there is noise. And here we will arrange it so that you might produce a program still, but we can arrange it so that this program has very low rank, and I'll show you why, and I'll show what rank actually means. And here, I might get another sample, and then I might produce more programs for that. And then what the algorithm does is that actually it collects all of these programs that were obtained by many, many samplings, and we are going to now weight these programs by the number of inputs for which these programs produce the correct outputs. Right? So even though this P2 was produced by only 2 inputs, I can now run the program on all of the inputs, and I can evaluate how many inputs this program produces a correct output, right? And using that weights, I can then generate a covering sequence of programs, which is a small number of programs that cover a large number of inputs. So now I can generate, so this is how the algorithm works. Does it clear what this algorithm does? So our experience has been that doing this has the same effect as regularization. Here, in some sense, sampling is used to deal with random noise, and high-ranked programs are produced for noise-free samples. And either low-ranked programs or no programs are produced for noisy samples in the same cluster. Like, for example, right, this particular program that I showed, maybe it handles only 2 of the inputs. As a result, this program does not have a high rank, and it doesn't make it into the cover that I finally generate. So the sampling followed by coloring, makes synthesis work more like a regularizer. That's the first interesting observation about the system. And by controlling the expressiveness of the domain-specific language, we can do something much like bias-variance trade-off. Everyone here knows what bias-variance trade-off in machine learning is, right? So for example, right, this particular example I mentioned, you can actually design a language which takes a string as just an array of bytes and allows you to index into the individual bytes of the array. So the programs there might look like return the string that is from the 10th position to the 15th position. That could be a program in this language, right? But such a programming language would allow you to process inputs which are even from different clusters, because you would generate some program which overfits and generates a program that handles both these situations. But what you could do is that you could design a different language, much more like a language which has a higher order concepts like keys and values. Where corresponding to keys, there are values. And then you look at a value corresponding to a key, and in that language, those kinds of degenerate programs cannot even be expressed in such a language. And using that, you can actually make a domain-specific language, which is, as your intuition as a programmer, the kind of constructs you need to write meaningful programs. And using that, you can actually do the same kind of bias-variance trade-off in this system. The final observation I'll make is that in our experience, this kind of systems deal with random noise very well. But these kinds of systems inherently have another kind of noise called systematic noise. And systematic noise comes in because labels are often generated by scripts. You write a script that actually goes over all the web pages, crawls them, and generates what you think of as candidate outputs. And those scripts have bugs in them. And as a result, the noise is just pervasive and systematic. And these kinds of systems NDSyn doesn't have to deal with it. But there's something else you can do inspired by programming languages literature, where programming language people have these things called types. Types are constraints on data items, which define which data items are well-formed and which data items are not well-formed. So if I want to extract a date, I can actually write a program which, given a date, will tell you whether it's a valid date or not a valid date. The date has to be within a certain range, month has to be within range, and so on. And so what you could do is that you could actually, on these labels, run those kinds of types and then figure out which labels are correct and which labels are not correct. And then what you can do is actually you can take these programs. Once you have these programs, you have something very interesting, which is that you have now 2 representations of the system. Yes? So, okay. Okay, very, very good. So what I mean by noise, actually precisely mean by what, so I'm assuming that there's an oracle that knows what the correct label is for every input. And if I have a label that is incorrect, I call it as noisy. So I'm assuming the existence of an oracle who can label everything correctly. And labels that are labeled incorrectly means that there's some noisy process that is actually labeling that. That's noise. By random, what I mean is that, if I think about how that noise got generated, if I can write it as a deterministic program, I would call it a systematic noise. If I need a coin toss to even be able to generate those labels, I will call it as a random noise. Oh. I see. Actually, one of the reasons why I thought giving this talk here is useful is that I'll show you my paper. There are actually many things I'm able to prove about specific subroutines of this system that we have designed. But we don't have theorems about this overall system. And I think in order to be able to prove theorems about them, I think I may have to actually understand and characterize the kind of noise and so on. So my secret agenda is behind, again, giving this talk was actually sort of get some sense for what kind of theorems I might want to state about the system and what might I want to prove about them, right? And I think I don't have such theorems yet. And that will be useful for me to understand and how to prove them. Yeah. So going back to where I was, so now I have two representations of the system. One of them is a machine learning model, and the other is actually a program, a set of programs. And these are both, capable of doing this job, where if I get a new input, I can actually run it through the machine learning model and get the label, or I can actually run it through the programs and get a label. And in those places where the two labels agree, I can actually increase the confidence that I have in the labels. And the places in which the labels disagree, I can actually invoke the oracle and ask the oracle what is the correct answer, which is actually I might have to ask a human what the correct answer is. And this is how we close the feedback loop in the system, right? So this system is actually what we call as a heterogeneous data extraction framework. Yeah, so basically, right, my desire is actually to produce the best programs with the least number of calls to the oracle. That's the goal, right? But what I don't have theorems on is actually, by doing various assumptions, can I actually bound? Like if I have this much random noise, can I actually put a bound on the number of calls I need to make an oracle? Those are the kinds of theorems. If any of you want to collaborate with me to prove them, I would love to work with you to prove them. So those are things I don't know how to do. But let me show you something very interesting, right? Let me show you, empirically, I find that these algorithms work very, very well, right? So let me show you the results that we have. In order to understand the results, I'll describe some metrics to you. There is a ground truth F, which the oracle knows. And the extracted programs I have, F star, are some approximations to F. They're not exactly F. And I have the usual measures of precision and recall, where precision is a fraction of the things that F star, bottom means it doesn't have produce an output. The fraction of the outputs that F star produces, which is actually correct, is precision. And recall is the fraction of the actual outputs that the oracle knows that I produce, right? It's very clear, right? So that's precision and recall. Precision is out of the things that F star produces, how many of them is correct? And recall is how many of the ground truth can I actually recover, right? And then this number they use in IR. This is some inverted harmonic mean of these two things. That's what this is. Let me show you some results, right? So this is actually, we are trying to extract scores in 30 different fields from this data. And in 24 of them, right, it just dramatically improves the noise, right? Like the way to read this is, this I'm going round and round. This is the precision recall from the machine learning. And I feed this to synthesis, and I feed this to machine learning again. And you can sort of see that it sort of like snaps to one. It snaps to one here, it just improves. In 24 of these 30, right, I find dramatic improvement using this. Actually, also a very interesting question for which I would like to get a theoretical characterization is, when I do this loop, under what circumstances will the noise get amplified? Under what circumstances will the noise get crunched down? And that's what I meant by random versus systematic. I would like to get mathematical characterizations of them. And I don't know how to do that yet. So I think those are kinds of things that I would love to learn from you guys, how to do that. But I find empirically that it works in a lot of cases. And another thing that we have done is this thing about bias-variance trade-off, where this FE, by controlling the language, the domain-specific language, what we can do is this FE is this full text language which has array indexing and so on. This LT is a very carefully defined language. And by using a carefully defined language, I can get much higher precision and recall than a language that is actually not carefully done. So, and I would like to understand and formulate theorems about this as well, and I don't yet have all the tools to do that yet. So there's a paper at PLDI. PLDI stands for Programming Languages Design and Implementation. This appears there. You can download this from my webpage. There's an ongoing interaction we have with the product team that builds this machine-to-human email extraction to incorporate it inside the system. I mean, those are the kinds of things that we are doing. So I'll show you also one more example, which is very of the same form, so sort of get you a sense for how pervasive this problem is. So together with Monojit Chowdhury, who's a NLP expert, is a colleague of mine, we are working on this problem. This is called a grapheme to phoneme. And grapheme to phoneme is actually, you have some orthographic text. You want to convert it into phonemes, which is phonetic text, so as to feed it into a text-to-speech synthesizer in order to speak it, right? And this is, Bachpan, and this is Tamil. It's called Kedupa. And currently, to start linguistics have done this using hand-coded rules, because every language has a rule on how phonetics works in the language, and you could write it down. But lately, like every field, this is being disrupted by deep neural networks, where people don't write rules anymore. They just get a huge amount of data, which has this, and then people learn a deep model, and that's actually what people are using these days. But like many deep models, one of the problems that these have is that you generate a deep model, and then the model doesn't quite work right. It doesn't handle all the inputs well, and then you don't quite know what to do, because you can't change the program. And this is the same situation as the machine-to-human email. Because you don't understand what it is doing, you can't change it to do what you want. This is a very difficult problem that these systems have. Here's another one. Again, text-to-speech. If you want to have a text-to-speech system, you want to pronounce this as 1920. You want to pronounce this as 1902. You want to pronounce this as 2001. That's what humans would like. So can you write a program which, given this as input, produces this as output? Again, actually, you can actually do that using deep learning, or you can do it with rules. But if you have a deep learning system, can you actually automatically generate the rules from it? And it turns out actually that using this NDSyn, you can actually take examples, chop them up into trigrams, generate the training data using a deep model, and then use NDSyn to actually generate rules, so as to find equivalent rules to understand the mystery of actually what's happening inside a deep neural network is actually possible. And this is under submission to an NLP conference. And I could share preprints with you privately if needed. But to me, actually, this is why I'm very fascinated by this, right? So I find it very fascinating that using these approaches, I can now put a machine learning model and using a synthesis, a program together, and I could have two equivalent representations of the ground truth that is there. And it's very fascinating to me because as a programming languages person, I can take the programs that come out of it and rely on decades of program verification research to actually reason about these programs. Whereas actually the machine learning model, people don't quite know how to understand what these models are, how to reason about them, make a statement that for all inputs you produce a particular output. Our understanding of our ability to do that is actually far less in the machine learning model domain than in the program domain. So so this is just our work. I want to conclude by just giving you a little bit of what other people are doing in this space. The space itself is very interesting, the space between synthesis and broadly programming languages and machine learning. This is work done by my colleagues, Pratik Jain, Naga, and so on. So in a program synthesis system, as I mentioned, because the inputs, like a specification like this one, you only give two inputs and produce an output, we call it as under-specification, because actually there are many, many solutions for it. There are many programs that can satisfy the specification. Because there are many programs, ranking is a very important thing to do, because you need to rank the programs by which programs are likely to not overfit, which is actually, they are just talking about the specifics of that example, but work for other examples, right? And so Pratik Jain and Naga, together with Sumit, have actually come up with ways by which you can actually learn the ranking function using machine learning, right? And prior implementations of PROS used hard-coded ranking functions that understood what the domain-specific language is and which programs are more likely than the others. So what these guys do is that they now train the ranking function using data. And they also use machine learning to even do pruning about, when you search for the programs, you can do branch and bound and figure out which branches to even explore or not explore. And you could do that using machine learning, right? There is a very interesting field called neural program induction, where the output of training is actually not a neural network, but actually a program. And these systems have a characteristic that they typically have an encoder-decoder architecture, and the input is encoded into some vector representation using an encoder, and the decoder actually produces a program that you can actually run. So very, very fascinating things, and I think this is quite related, though since this whole thing is a neural network, I personally find it I can't understand what these papers are doing, even though the math is clear what they're doing, but I can't say anything about the meaning of what these things produce, much like I can't say that about any other neural network either. There is a very interesting field called automatic differentiation. And it's a very important field because DNN frameworks like TensorFlow, PyTorch, what they allow you to do as a programmer, they allow you to write neural network architectures of very different configurations. And they automatically generate a training algorithm without you having to say what the gradient is. And in some sense, what they can do is actually they can symbolically write the formula for the derivative from the text of the program. And you can do it compositionally in the sense that from the components of the derivatives, you can actually calculate the derivative, much like the chain rule in calculus. And this is an extremely fascinating area. It is by no means completely solved in order to how to do this. And these are papers that I just, from the programming languages community, which actually talk about how to think about automatic differentiation. So I think that's pretty much it. I mean, to summarize, I hope I gave you a little bit of a whirlwind tour of program synthesis, starting from the non-elementary algorithms to the constraint formulation as a search problem, and the difficulty by handling noise and heterogeneity. And then I talked a little bit about supervised machine learning and how for heterogeneous extraction here we can combine them. And I talked about other things like ranking and pruning, neural program induction. And my personal interest actually is in verification. So I'm very interested, and I'm doing some collaborations now to use this kind of approach to actually verify neural models. So I invite comments and and also collaborations if you want to actually help me prove these theorems. I'd be very, very interested in collaborating with you.